All right, let's get started. So you have PS 11 out and due end of the week, and then PS 12 will come out, and that'll be the last one, almost to the end of the semester. Any questions or problems about anything? Yeah. Okay, remind me what that one is.
It's about, I don't know off the top of my head. I have to look it up.
It's the bounds of solid.
The feasible region stuff.
Oh, okay. So with the A and the B. I'll take a look, make sure we're on the same page. Oh, this. Okay. Okay, so what aspect do you have a question about? About the problem itself or about the definition of the feasible region?
I understand the feasible region, but I don't know something I can do.
Okay, so this is a linear program there, which is kind of hard to see. Let me. And it consists of, it's a very simple program, 3 constraints. The last 2 are easy to see. You've got x greater than or equal to 0, y greater than or equal to 0. So the feasible region is at most the upper right quadrant of the plane. And then you've got that constraint, ax plus by is less than or equal to 1. And that'll give you a line. And that also restricts the feasible region. And so what you're supposed to do is, for different signs for A and B, figure out is the feasible region bounded or unbounded or empty, in which case it's infeasible. And if it's unbounded, is there still a bounded optimum or not? So it's just a matter of graphing that for all 4 cases. So let's graph it for one case. Yeah?
Oh, just to recall, if it's unbounded, then there's no optimal solution, right?
No, it could be. For example, let's take the program x greater than or equal to 0, y greater than or equal to 0, and then we're going to try to minimize x plus y. Okay? So what would be if we do that, what's the feasible region?
The whole top right quadrant.
Right. The upper right quadrant's feasible. And we know that the optimum, if it exists, has to be at a corner. Well, there's only one corner. So if this is not the optimal value, then there is no optimal value. But what is the optimal value if you're trying to minimize x plus y?
0.
It is 0, 0 there. Now, if we were trying to maximize x plus y, same feasible region, but no optimum value. Okay? Now, what if we had x greater than or equal to 0, x greater than or equal to 0, y greater than or equal to 0, and then we added y less than or equal to -2. Okay, so do that. So we would have, so the y less than or equal to -2 is going to give us a line here. And so the feasible region would be the intersection of this one, which is from the first 2 constraints, and this one, which is from the last 2 constraints. The intersection is empty, so there is no feasible region. Okay? What would it look like if, what would we have to get, what constraint could I add to get a bounded feasible region? Let's get rid of that constraint and add a different one in. It would be a simple constraint, yeah.
Y is less than 100 and x is less than 100.
Yeah, we could say y less than 100, x less than 100, or we could give a single constraint, which might be x plus y less than or equal to 100, for example. In which case we would have a diagonal line that intersected at, y equals 100, x equals 100. And in this case, what would be the feasible region?
Inside that zone.
In there. And then again, the optimum has to be at one of these points. Since it's bounded, there will be an optimum. And in this case, what is the optimal solution?
100.
Yeah, either one of these, 100, 0 or 0, 100 are equally large. We're trying to maximize x plus y. And in fact, anything on this line right here is going to work out the same. Okay, so the gist of the problem is you've got the program that says ax plus by. What was it? Less than or equal to 1. So you just need to do what I've done, graph it, and you got 4 cases, one, for depending on the signs of A and B. So you just figure out, is the region graph it and see if the region's empty, is it bounded, unbounded, and so on. If the A and B are causing you trouble, just substitute numbers. 2 and 5, something like that. Any other questions? Yeah.
Did we talk about the linear one, which ought to be solved, and the absolute error?
Okay. So you're supposed to write a linear program to. Well, let me do it that way. Okay, the idea is you've got a 2-dimensional plane. I'm not going to draw a feasible region on this one. This is a different kind of plane. And you've got some points that roughly follow a line. And it's a best fit problem. So you're trying to find the equation of a line that minimizes what? Yeah.
The sum of the residues.
Was it the sum or the max? The max of the residues. Yeah, I think it was the max. So basically, to keep the problem simple, normally if you're doing a best fit like this, you'd be interested in the distance of the point from the line. Like that. But that's not how distance is defined here. It wouldn't be a linear program if we did. We'd have to use square roots. How is distance defined for the purposes of the problem? How do we measure the distance between a proposed line and these points? Yeah?
The point which is furthest away from the line, or the distance between them is...
Well, right, but the question is, how do I define distance from point to line?
the vertical distance between
Right.
a point and...
So the distance is just the vertical distance here. Okay? So essentially your variables, you're given the actual coordinates of the points. So your variables are just the two, the y-intercept and the slope from the equation of the line. So you've got to solve for those two variables in a way that minimizes the largest of these error bars. So for example, in the case we're looking at, we'd sort of want a line that sort of tips up a little bit more because we need to make this one here, that long one is a little bit smaller. So we sort of need to move the line up or rotate it or something to make that error a little bit less. So you've got the equation like y equals mx plus b. Those are your variables, m and b. So you need to write a program that puts constraints, uses constraints to express the deal that we need to minimize the error. It's hard to say a whole lot more without just out doing it. Okay? But let me do this part. Is this a minimization problem or a maximization problem? Okay. So we got to minimize. The objective function is something we want to minimize. Now, what is it we want to minimize? The error. We'll call that E. Okay? We want to minimize the error E. Now, what can you say about the error? See, I think the mistake a lot of students make is now they want to define the error. You don't have to define the error. You just got to put bounds on the error. That's what a linear program is good at. So there, I've written the objective function for you. You just got to find a way to put bounds on that error E. So that you find the minimum error subject to some bounds. So you just need to add constraints here that involve M and B and E in these points here. All right. I'll let you think about that. Offline. Are there any other questions? Okay. Okay, I did start that. All right, back to this. All right, this is what we were talking about last time. These two sets P and NP. And just to remind you, P is the set of all search problems that can be solved in polynomial time. So the way a search problem works is there's some problem instance that goes in and a solution comes out. That's a very general description of a search problem. And to qualify as a member of that set P, it has to be a search problem, and furthermore, it has to run in polynomial time, O of n to the b for some constant p. So n squared algorithm, n cubed algorithm, n to the fifth algorithm, n log n algorithm, all those count, just not exponential. So we're very familiar. We've studied lots and lots of search problems that run in polynomial time. So lots of familiar things in that set. Then there's the larger set, NP. NP contains P. And NP is the set of all search problems that can be, whose solution can be verified in polynomial time. So we're not requiring that you be able to, for P it's more stringent. You have to be able to actually find the answer in polynomial time. For NP, all you have to qualify is if you're given a description of the problem, the graph you're supposed to search or whatever, the number you're supposed to factor, and you're given a solution, a proposed solution, like a path in the graph or a factorization of the number, you need to be able to quickly say yes or no, is that a solution to the problem? So that's a weaker condition. Clearly, if you can solve it in polynomial time, you can verify a solution in polynomial time. This is a weaker condition. So we're just asking, can you check someone else's work in polynomial time? So that's P and that's NP. And we're trying to understand the relationship between those two sets. They're both sets of problems. Okay? So there's no point in going further if there are any questions remaining about the definitions of those sets. What's the open question about these two sets, P and NP? Yeah?
Is it the same set or not?
Are they the same set or not? Are there any problems that are members of NP that are not members of P? Are there any problems that you can whose solution you can verify in polynomial time, but which you can't actually solve in polynomial time? And that's been an open question since 1970, so almost 50 years now. There was a young professor at Berkeley, University of California at Berkeley, named Stephen Cook, who first developed this theory and first asked that question. roughly at the same time, but a little bit ahead of a Soviet scientist named Leonid Levin, who sort of doing the same thing in parallel, which often happened in those days. And so Cook sort of defined these sets P and NP and started investigating them. And for his trouble, he was denied tenure at Berkeley. So he was basically let go after 6 or 7 years because presumably people didn't appreciate his research. And so nowadays he's an esteemed professor at the University of Toronto. And Berkeley clearly made a big mistake that day. All right, so here's the question. Does it look like this? So is our world organized like this, where NP, and we know that P is a subset of NP. The question is it a proper subset? So is it look like this, where P is a smaller set than NP, and there are problems like this number 2 that lie outside of P but lie inside of NP? Or is it more like, that, where the two sets are the same? And no one knows. So that's the that's the question people have been looking into for 50 years. Are the two sets the same? If they're the same, it means that all such problems, such as a traveling salesman problem, the NatSat problem, 3SAT, and on, that we've looked at, it means they all have fast algorithms that have not yet been discovered. So if P equals NP, there are these thousands of problems that people have studied and been unable to find fast solutions that would, in this case, turn out to have fast solutions. If they're not the same, it means that all those problems that I just mentioned actually require exponential time. Yeah?
I guess I don't understand why, if you solve one, because it seemed like completely different problems.
Okay.
Solve one, you can solve the rest.
All right. So traveling salesman problem, NatSat problem, 3SAT, they all have something in common. And that thing they have in common is they're all NP complete. Now we're in the middle of defining what NP complete means. You can think right now, just think of NP complete problems as being the hardest problems in that set NP. So NP complete are the hardest ones in the set. And it just turns out that what has been known, what Cook showed, is that if you can find a fast algorithm for any NP complete problem, that implies all the NP complete problems have a fast solution. And if you can prove that one NP complete problem, you pick one NP complete problem and prove that it requires exponential time, it implies that all the NP complete problems require exponential time. Even though they're very different, they share this one characteristic. And they're either all can be done fast or they all can't be done fast. It's not like we're going to find a fast solution for traveling salesman problem, but not for 3SAT. If we solve one, we've solved them all. And we're just, what I'm working up to is a definition of how you show something is NP complete. Now this is, the key to the way you define NP completeness involves this idea of reduction. And this is what we were talking about at the end of class last time. So the idea is you want an algorithm for A. You've got some problem A you want to solve. You want an algorithm for it that takes in an instance, a graph, a number, a factor, whatever, takes some input, and it either produces a solution or it says there's no solution. And the way we're going to do it is by making use of an algorithm for a different problem. So we're just going to assume that there's this problem B and we have an algorithm for it. And then we're going to use that algorithm to solve problem A for us. And that's, I was observing last time, that's the kind of thing you do all the time when you use a library. You've got some problem you want to solve. There's some method in the library, your language's library, that comes close to solving your problem, but not quite. So what do? You take the inputs for your problem A that you want to solve, you modify them slightly, feed them into to the method B, get a solution out, maybe modify the solution slightly to get an answer for A. That's just programming. And so to finish out the picture here, what you have to do to create that reduction is you have to implement a method F that transforms input that's intended for A into input that'll work for B. And then, if it turns out there's no solution for B, you report there's no solution for A. Otherwise, if you get a solution for B out, you generally transform it so you've got a solution to the original problem. That's just a pictorial diagram of what programming is like. And that's what we call reduction. And before I get to we didn't look at this last time. So I've added this slide in. Let's define a really simple reduction. Let A be the problem of finding the largest index in an array. The index of the largest element in an array. So you get an array and you find the index where the largest element resides. That's easy to solve. Let B be the problem of finding the index of the smallest element in an array. Can you reduce A to B? Suppose you had a implementation of B sitting around and you wanted to use it to solve problem A. Can you define a reduction from one to the other? How could you trick B into solving A? Yeah.
Reverse the signs of, if they're integers, you could reverse the signs of everything in the array and cross it to B and get the answer.
Right, that's the idea. So this is what you would do. You would take whatever array was being sent into to your algorithm for A and just flip. I wrote the wrong thing. What should f of A say there? Let's fix it. So I added the slide, but I added it wrong. Okay? So what he said was f of A returns the result of. What did I do? Okay. It gets in this mode sometimes where I can't type from the keyboard when I'm running these slideshows. So I'll just have to remember to fix it after class. Now it gets in a mode where it won't show anything. Right, I'll just do it this way. F of A returns the result of negating every element in A. And H of I, we get an index out. So instead of looking for the largest element, we reverse the signs. B finds the smallest element and spits out that index. There's nothing we need to do with the index. So H of I just returns that. So that's a very simple reduction. Maybe not the way you would choose to find the largest element in an array, but it's intended to illustrate the idea of a reduction. Can you think of how we could tweak the problem a little bit so that we'd have to do something with H? Yeah?
You could, if it were Java, pass comparator that compares it the other direction.
Yeah, I'm not sure that really had to do with the index, though. I had another example in mind when I wrote these slides, which is why I made that typo, because I tried to simplify it. Imagine if what A did was it's supposed to return the index of the largest element, and if there's multiple largest element, it returns the one that occurs first. And let B be the one that returns it finds the smallest element, and if there's a tie, it returns the one that occurs last. Okay? So in that case, what would f of A have to do in order to reduce to B?
Negate and reverse.
It would have to negate and reverse the array. And then you would get the index. Now, there'd still be nothing to the index, would there? Yeah, there would. So with the index is supported by B, what would you do?
You have to reverse A and then find that same element.
Yeah, let's make this more concrete. Suppose this is your array. 1, 3, 2, 3, 1. Okay? So if you feed that to A, what you want to get out is this index 1 right there, is the largest element, the leftmost largest element. But instead, let's solve it with B. Oh, this is awful. What a terrible example.
Palindrome.
Okay, because it was a palindrome. So to get B to solve it, what we're going to do is reverse and negate the elements of the array. So we get 0, -3, -2, -3, -1. Now, what index is B going to return? Remember, it's going to return the rightmost smallest element. Right. It's going to return that element right there, index 3. And so we don't report 3 as the answer to the original problem. What do we have to do?
You have to report the index.
We have to turn that 3 back into a 1.
So you can just subtract the length of the array from that index, right?
Right. You subtract the length of the array and then add 1, I think, something like that. Yeah. So it's just you just basically have to reflect the index around the center of the array. So that requires a little bit of work setting up to call B and a little bit of work recovering from calling B. That's a reduction. All right, let's see if this is loaded. All right. Okay. Now, this is the answer. This is what we're looking at last time when class ended. Let's do a reduction. Okay, so here's one problem, is to find a Hamiltonian path. So a Hamiltonian path in an undirected graph is, the input is a graph and 2 vertices. And the question is there a path, or find a path from the first vertex to the second vertex that visits every vertex exactly once? So does this graph contain a Hamiltonian path that starts at A and ends at B? Let's see. Yeah, it has a Hamiltonian path. Does it have a Hamiltonian path that begins at E and ends at F? No. You start at E, if you go here, you're stuck. No way to get to F. If you go here, there's no way to take in B and A and then get an F at the end. So this doesn't have a Hamiltonian path. So that's Hamiltonian path. The Hamiltonian cycle we've looked at, that's just you start at a vertex and you want a path that visits every vertex exactly once and then goes directly back to the start. So does this thing contain a Hamiltonian cycle? No, I don't think so. Yeah. It has dead ends. If they're dead ends, it's not going to be a cycle. All right, we want to reduce the Hamiltonian path problem to the Hamiltonian cycle problem. In other words, we want to know, does this graph contain a Hamiltonian cycle? But we happen to have a Hamiltonian, we want to know if this graph contains a Hamiltonian path from A to B, let's say. And we happen to have hanging around an algorithm that'll tell us whether there's a Hamiltonian cycle or not. So we want to trick Hamiltonian cycle into solving a Hamiltonian path problem for us. And what was the solution we came up with?
Adding an extra point for a vertex between A and B.
Right, so what we did was the transformation we made was to add a new vertex x and have x have an edge to B and an edge to A as 2 endpoints. And then we asked the question, does this modified graph contain a Hamiltonian cycle? And my claim is this will contain a Hamiltonian cycle if and only if the original graph contained a Hamiltonian path from A to B. So, yeah.
With this, you're asking if there's a path from A to B. So every time you use this cycle, you basically have to check every node, right?
Right, a cycle would have to visit every node once.
Right, and so you have to check A to B, like A to C.
Well, we don't really care what's going on. The question is there a graph we could create such that when we did this transformation to it, say a graph we could create that did not have a Hamiltonian path, yet when we added on this extra vertex and edges, the resulting graph contained a cycle. Is there a way to cook up a graph like that? Because what we're counting on is that when we do this transformation, we're only going to find a cycle if the original graph had a path. What's the argument that if this has a cycle, the original graph has to have a path from A to B? Yeah.
The only way to get the
So any cycle is going to involve, at some point, going from B to X to A. There's no way around it, or from A to X to B. Right? Because the only way to get to X is from one of these, and the only way to get Alice from one of these, because we added those edges in. And so if there's a cycle, we just take that cycle, we cut these edges out, and what we got left is a path from A to B. So what's the transformation coming in? What does F do? When F is given the y part of this graph, how does it transform the problem? Well, actually, the incoming question involves this graph and the two endpoints A and B. So that's the input to the path problem. We're given a graph, a starting vertex, and ending vertex. So what does F do? Yeah, just adds this yellow stuff in to the starting and ending vertices we're given. Then we try to find a cycle. If we can't find a cycle, the path reports that, and then that's just reported as the cycle problem says no solution. There was no solution to the original path problem. But what if the cycle method finds a solution to this? How do we produce the path? The cycle thing will spit out some vertices in order. So it might say B, E, C, D, F, A, X is a cycle. Yeah.
Just take X out of the
Yeah, you take X out of that solution, you might have to rearrange it to get A at the end and B at the beginning. So if it went E, B, X, A, C, F, well, that's not going to work. Anyway, it may not be quite as simple just removing the X, but you take the X out, maybe rotate the order of the vertices a little bit so you get A at the beginning and B at the end, and you got your solution. So that's an example reduction. Now, the question last time was, couldn't we do something simpler? Let me go back. The proposal last time was, why do this? Why not just put a yellow edge from A to B? Why do I add this vertex this way? Why not just add an edge from A to B? Right? Here's the reason that doesn't work. Let's consider this graph right here. Suppose you're interested in whether or not there is a Hamiltonian path from A to B. Okay? Is there a Hamiltonian path from A to B? No. Now, there are two problems with simply adding an edge from A to B when we do the reduction. One is there may already be an edge. So that's just sort of a technical problem. The other is more serious. What happens if we do the reduction the other way? We add an edge from A to B here. And then we ask the question, does this graph have a cycle?
Yeah.
The answer will be yes. The answer doesn't, there was a cycle to start with. Before I added that edge, there was a cycle. I add the yellow edge, there's still a cycle, but there's no path. There never was a Hamiltonian path from A to B in the original graph. So we get the wrong answer to that. It's a bad reduction. We would say, if we use this reduction, we'd be reporting that this graph had a Hamiltonian cycle from A to B, a Hamiltonian path from A to B, and it doesn't. So that's why adding just that edge. So what is it that makes what is this construct forcing if that other edge doesn't force? Yeah.
It makes it so there isn't a path directly from A to B.
True. It makes it so that there is a path direct from A to B. But I have a different way of describing it in mind. Yeah.
If there's a path directly from A to B, you're not allowed to take it
Right.
because you have to go to X instead.
By doing it this way, when you find a cycle, you're forced to include both these yellow edges in a cycle. You're forced to go from B to X to A, or from A to X to B, which means that after you find the cycle, you just splice out these edges and you've got a path left. If we add the edge directly from A to B, we're not forced to take it. And so we may find a cycle that doesn't involve finding A and B consecutively. So it can be tricky to get these things right. Okay, so this is just in symbols what we just did. So this is, again, the reduction. The input is a graph and two vertices, the endpoints of the path we're looking for. F just adds a new vertex in those two edges. Then we run the Hamiltonian cycle algorithm. When we get an answer out, we just remove x and its edges from the path that we get back, and maybe fiddle with it a little bit, but get things in the right order, and we're done. So that's just, to define the reduction, we just got to give the f and the h. All right, now, let's do another reduction. That last reduction that we did, in fact, both reductions we've done have been between problems that are pretty similar. These are pretty different. Let A, we're trying to solve the subset sum problems. Who could tell me what the subset sum problem is?
I think you introduced last time as find the subset that adds up to the sum and then I can.
Right. So you're given a set of integers and a target integer m, let's say, and you're trying to find a subset of the input set that adds up to m. So pretty simple to state. And you could solve it by looking at all possible subsets. If you have an array of length n, how many subsets are there? 2 to the n. So that's your exponential right there. If you try to look at every possible subset, it takes exponential time. So let A be the subset sum problem. So that's a question about sets of integers. Here's one. Let B be the problem of finding a path in a DAG that has a particular weight, particular total weight. So you're given a weighted DAG, and you're just asked, is there a path in this DAG such that if I add up the weights of all the edges I traverse in the path, it adds up to some target m? Okay? Can you come up with a reduction from one to the other? Can you find a reduction from the subset sum problem to the DAG path problem? And here it is in pictures. There's our set, K1 through Kn. We've got a set like that. We have a goal m. What I want is draw me a DAG down here, a weighted DAG, such that I can solve the DAG problem, and that will give me a solution to the subset sum problem. I want you to take a few minutes. Talk to people around you. Don't look at the next slide. And see if you can come up with a reduction. So you have, yeah.
I think before then, the subset sum, you can have like a K1, K3, and then Kn as a subset.
Yeah, yeah.
You've already got an answer.
Okay? So, yeah. Just imagine you have a library method that solves this DAG problem, this DAG path problem, and you want to use it to solve the subset sum problem. So how can you turn that stuff into a DAG, solve the DAG problem, and take the solution you get and turn it back into a solution for that? Okay, let's who has an idea? Let me get back by the wall this time.
So the set could represent the result of a topological sort, so you could turn it into a DAG with K1 representing the weight from the first node, K2 representing the weight from the second node, and so on.
All right, so you're doing something like this, like that?
But then also put a path from the first node to the third node with weight K2.
Okay. And, okay, so we have K3 here. So do we need an edge from, what other edges do we have to have at that point?
The first and second vertex going to the fourth vertex.
Okay, so we need an edge here
Yeah.
with weight what?
K3
K3. And then an edge here,
with the same weight.
K3. All right, so let's stop there and see. His idea is, let's see, if I go from here to the end, that represents K3. Right? If I take this path, the weight's going to be K1 plus K2 plus K3. If I go like this, I get K2 and K3. So he's trying to construct it so there's a path corresponding to each subset of the original, of that set. So if I go from this vertex to that vertex, there are lots of ways to do it, but there's going to, each way corresponds to a different set of, a different subset. Okay, does that work out? Let's see, K1, K2, K3. What if my solution was K1, K2? Now there's a path here, K1, K2. Just that path right there corresponds to adding K1 and K2. K2, K3, what about K3, K1? K1, K3. Right? What about the empty set? What if our goal is 0 and the empty set is a solution? Yeah?
You just have like an arrow going back to the beginning for that?
No, it wouldn't be a DAG with an arrow back to the beginning, but we could just have a path, the empty path from the vertex to itself has total weight 0. So yeah, we can make this work. It's a little hard to draw, especially as the graph gets bigger. Just got to make sure it doesn't require an exponential number of edges, which I don't believe this one does. Okay, that works. Who had a different idea? All right, let me show you mine, which is, which is a little bit simpler. Here's my reduction. I just make, n plus 1 vertices, and I have K1, K2, K3, K4, and Kn. And then I have a way to bypass these edges. So I can bypass edge K1 by going down here at weight 0 and up there at weight 0. Like that. And I claim that any path, any subset up there corresponds to some path down here. And any path down here we can turn into a subset up here. So let's say that it turns out that K1 plus K4 plus Kn equals M. What path down here is going to have that weight, K1 plus K4 plus Kn? Yeah?
So you go to K1,
So we do this,
and then you follow the zeros.
skip, K4, skip, Kn. So that path from beginning to end, its total weight is K1 plus K4 plus Kn. So essentially, I've given a way to bypass. Now, suppose that you find out that you solve this problem and you find out that the solution is to go from here down to there, down to there, down to there, down to there, and then along the spine. How do you turn that into a solution for the original problem? You get a path, which is going to be a bunch of edges between vertices. How do you turn that into the solution you wanted for the original up there? Yeah.
Your nodes can contain some information as to what is which. So if you're at the one before K3, you can know that, I'm taking K3.
Yeah. So your nodes, the vertices will be labeled, and so you'll know which edges were added. So basically, you're going to come up with a path whose total weight is M. You just throw away all the edges, all these 0 edges, and you keep the weights of the edges that remain. And that is a solution to that problem up there. Yeah.
Would this reduction require your K1 through Kn to be non-zero?
Okay, would it require would it work to have, if K1 or something was 0 is the question? Because I said we're going to throw away all the 0 edges.
If it's 0, then it doesn't matter if it contributes to the.
Yeah, I mean, let's say K1 were 0, and we found a solution that involved adding K1, K2, skipping the rest, and adding Kn. Then we throw away all the 0 edges, all that's left is K2 plus Kn. Well, that's still a solution. You know, if there's a 0 in that set, then any solution we find is going to have another solution. There's going to be a solution with the 0 and one without, so it doesn't matter. Yeah?
So is the K1 through K sub n, are those subsets of the original
No,
set,
no,
or
those
those
are-
individual values?
These are just the numbers in that set up there.
Okay.
So there are K numbers in that set. K weights along the spine here. And then I have these bypasses. So that for any subset up there, there's going to be some path down here corresponding to it, and vice versa. There's only going to be a path of length m down here if there's a subset whose total sum is m up there. That's the gist of the reduction. So, the best known solution to this problem takes exponential time. Now, suppose you could solve this problem in polynomial time. Would the total solution be polynomial time? We have to remember, so if we can solve a problem like this in polynomial time, would the cost of the reduction be exponential? No. Taking that set, producing this, is going to take time proportional to the length of that set. That's polynomial. After we found a solution down here, returning it back to a solution up there, that's fast too. So if we could solve this in polynomial time, we would be able to solve that one in polynomial time. So that's the key idea in the definition of NP completeness. And this is what this slide summarizes. So, turns out we're not interested just in reductions. We want reductions where the f and the h operate in polynomial time. So we need fast reductions. We don't want exponential time reductions. So imagine if we've got an algorithm for f here that is O of n to the a. And then we have, I got that wrong. F right here is O of n to the a. The algorithm for b is O of n to the b. And the algorithm for h is O of n to the c. The question is, what bound can we put on the entire algorithm that's inside the box? Now it's tempting to say, okay, first you run an O of n to the a algorithm, and then you add an O of n to the b algorithm, and then you do an O of n to the c algorithm, and you figure out what's bigger, a, b, or c, and that's your exponent, so it's going to be polynomial. Why is that misleading? Why is that wrong, in fact? Let's say we're cascading so we have an n to the, let's say an n cubed algorithm for f, then we have an n squared algorithm for b, and then we have an n to the fourth algorithm for h. So you might say, okay, we run those algorithms in succession, so the whole box, the whole composed algorithm is going to be O of n to the fourth. But that's not right. Why could it be worse than n to the fourth? Yeah.
Could the prior stages modify like the size of the?
Exactly. That n cubed algorithm, if the output is, okay, so let's suppose that the input coming in here is of size proportional to n. Now, if f produces output that's size proportional to n, and b produces output of size proportional to n, then that's the answer. The problem is f may produce, may increase the size of the input. So could F potentially produce an exponential amount of output, in which case the composition is not a polynomial at all. Okay? I see a few people shaking their heads and a few people nodding their heads. So which is it? Can an n-cubed algorithm produce exponential amount of output? Yeah?
I'm going to say no, because if it was producing an exponential amount of output, you'd have to store that output somehow, which would require exponential rights to store that output.
Yeah. An n-cubed algorithm doesn't have time to produce an exponential amount of output. It takes exponential time to produce exponential output. Okay? What if I ask you to make 2 to the 100th marks on the chalkboard? That would be, I can't claim that there's a linear time algorithm by which you can make that many marks on the chalkboard. So you cannot, an algorithm can't produce more output than the time it consumes. So an n squared algorithm is going to be n squared, can't be n cubed in space. It doesn't have time to generate all that space. So if we feed if our input problem is of size n, how big is our output going to be at most from the F stage? N cubed. The next stage is going to produce, it's going to take quadratic time, so that's n to the 6th. And potentially its output could be that big. And so that n to the 4th algorithm runs on the n to the 6th amount of input. And we got an n to the 24th algorithm. So when you compose these algorithms, the output can grow, yes, but it can't grow exponentially large. It's still polynomial large. So the point is, if F, B, and H are all polynomial time algorithms, their composition will be polynomial time. But instead of being n to the 4th, like we originally supposed, it could be as bad as n to the 24th. It can't be exponential. If you compose polynomial time algorithms, you're going to get polynomial time algorithm out. And that's all we care about. And this just says that in symbols. Okay, let's stop there, and then we'll define the set NP complete. Not stop there, we'll pause there. So we've got NP, which is a set of all search problems that can be verified in polynomial time. And we have P, which is a set that can be solved in polynomial time. And now we're going to find NP complete. And it's a set, which is the set of all NP complete problems. A problem is NP complete if it's, first of all, a member of NP. So NP complete is a subset of NP. So that's one thing. It can't be too hard. There are problems that are harder than NP. But this is no harder than any, it's, the basic thing is to think of NP complete as the hardest problem for each set NP. So a problem is NP complete if all other problems from NP reduce to it in polynomial time. Okay, so we've just defined polynomial time reduction. Okay, polynomial time reduction is when you can, you take one problem, you pre-process it in polynomial time with that f, you solve it, and then you post-process it in polynomial time, and you get an answer out. That's polynomial time reduction, when f and h are polynomial time methods. So there are an infinite number of problems that belong to NP. But something is NP complete if every single one of those problems reduces to this problem x we're looking at. If that's the case, then we say x is NP complete. These are all NP complete problems. Every problem from NP can be reduced in polynomial time to 3 set. Similarly, every problem from NP can be reduced to the Traveling-Salesman problem. It can be reduced to longest path problem, independent set problem, Hamiltonian path problem, net set problem, subset sum problem. These are all NP complete problems.
So because of that, that's why we say that we solve any NP complete in polynomial.
Exactly. Suppose, now that you know this, every problem you pick from NP reduces to each one of these. So suppose you found a fast algorithm, a polynomial time algorithm that solved the Hamiltonian path problem. How could you, now that you know that this can be solved fast, how could you argue that 3-sat could be solved fast? Yeah.
Just reduce 3-sat.
Right. If you had a fast implementation here, this is now problem B in our diagram. This is problem A. We would take it, we know that 3-sat reduces to Hamiltonian path problem because everything reduces to Hamiltonian path problem. So we would take our 3-sat instance, convert it into a Hamiltonian path problem instance, solve the problem, and then convert the answer back into an answer for 3-sat. Each step would be polynomial time. It's because we know there's a polynomial time reduction and we're assuming that there's a polynomial time solution to Hamiltonian path problem. So if one of these problems fall, they all fall.
Is this list larger, by the way, or is this?
Oh, it's much larger.
Okay.
Okay. So what Cook did was he defined the sets P and NP and NP complete. And he defined NP completeness. And he started proving that problems were NP complete. And then other people picked it up. And so at first, in the early 70s, it was tough. But nowadays, I've seen, high school science projects that prove things are NP complete. So it used to be, only the top theoretical computer scientists did it, and then, PhD theses were doing it, and now high school kids are doing it. Yeah.
Are we saying that every NP complete problem can be reduced to the Hamiltonian path problem?
Yes, any problem from NP can be reduced to the Hamiltonian path problem, and all these problems are from NP. So in particular, every NP complete problem can be reduced to every other NP complete problem. Yeah.
So if we find a fast solution for a problem that's NP but not NP complete, does that mean these problems still remain unsolved?
Right. So we know plenty of fast algorithms for problems in NP. Right. Shortest path problem, assuming no negative cycles. We can solve that fast, but that doesn't give us a solution to the general shortest or longest path problems when you're allowed negative cycles. Yeah.
How would you prove that one of those is NP?
Okay. How would you prove? Okay. look at. How do you prove something is NP complete? How did Cook do that? Well, let me go on and answer that question. Okay? So first of all, here's if P is not equal to NP, this is the picture. This is what most people think is the picture. So we got this set P. These are problems that we know can be solved in polynomial time. Then we have this set, and think of distance from the center as being harder and harder to solve. These problems out here, in this area, are the NP complete problems. They're the hardest ones. And if P is not equal to NP, all these problems require exponential time. And then there'll be some problems in between that perhaps, actually I'm not sure if this is a given, but in this diagram, this would represent problems that are outside of P, but aren't hard enough to be NP complete. So, from what's known today, factoring sits here. The factoring problem has not been shown to be NP complete. The problem, finding the prime factorization has not been shown to be NP complete. It's also not shown to be a member of P. So it may require exponential time, it may not. Yeah?
How do you know that factoring has been proven to be incomplete?
How do I know that? I guess from reading.
What separates it from something that has been?
Well, it's because the other problems people prove they're NP complete and publish papers about it. It would be very a good thing if people prove that. It would be nice if people prove factoring is NP complete. What would be the practical importance of a proof that factoring is NP complete? Yeah.
It means that all of our encryption algorithms can't easily be broken.
Well, it gives us more. So RSA depends on the assumption that factoring is hard. But factoring has not been proven to require exponential time. If we prove that factoring was NP complete, that would be additional evidence that factoring is hard, because most people believe that P is not equal to NP. And if P is not equal to NP, all the problems in here require exponential time. If we could move factoring into here, it would just be more evidence that it's going to be hard. It wouldn't be a complete proof that it's hard. Yeah.
So obviously you can prove that something's NP or it's P or it's NP complete, but is there any way to disprove it? Would there be any way to without finding, I guess, a fast solution?
Yeah, I mean, I'm not very up on that about proving something is not NP complete.
Right. Yeah.
But yeah, that's something. People have gone so far as to, they want to study, people would love to prove P is not equal to NP. That's proven elusive. And so there are theorists that will prove properties of any eventual proof of P not equal to NP. So they'll prove that this particular line of reasoning won't work.
Interesting.
So they just nibble away at the thing, but they haven't solved the whole thing. So they have these meta proofs about the eventual proofs. Okay, so that's the set P, NP, and NP complete. So just to summarize, assuming P is not equal to NP, all of these problems are going to require exponential time. If P is equal to NP, then then basically all this collapses and everything is the same. Yeah.
So you're pointing to that NP complete problem, saying that they require exponential time. What about problems in set 2?
Okay. So these would be problems that require exponential time but aren't NP complete. And currently, factoring is such a problem, but it may be NP complete, it may be polynomial time, we don't know. Yeah?
So does that mean it hasn't been proven that factoring can be reduced into one of the NP complete problems?
No, certainly factoring can be reduced to an NP complete problem.
Okay, but
Everything from NP can be reduced to an NP complete problem.
that can't be the other way.
That's right, the other way is an interesting question. Okay? This is what I just said. If you discover a polynomial time algorithm for any NP complete problem, you will have shown that P equals NP. And again, that's considered unlikely because people have been trying, every programmer has the potential to discover this missing, this elusive algorithm. It hasn't happened. If P is not equal to NP, if you prove that, you will have proven that every NP complete problem requires exponential time. And I was asked, how do you prove a problem is NP complete? The way you do it is you show how to take a known NP complete problem and reduce it to problem X. So you reduce a known NP complete problem. So to prove factoring is NP complete, you would take, say, 3 set and reduce it to factoring. Not the other way around. Yeah?
So how was it proven that the first NP complete
Ah,
was NP complete?
yes. Chicken and egg problem. That's what Cook did. So what Cook did was prove the original NP complete problem, which was a variant of 3 set. And then from there, how did you prove the next thing was NP complete? So the original NP complete problem is called circuit satisfiability. It's basically given a Boolean logic circuit like you'd find in a computer. Find a way to set its input so true comes out the bottom. So he proved that circuit sat was NP complete. So how do you prove the next problem is NP complete? Yeah?
Reduce it to circuit sat.
Other way around. You reduce circuit sat to it. Okay? Now you have 2 NP complete problems. How do you prove the third one? You reduce, you got 2 to choose from. You reduce one of them to your new problem you care about. Suddenly there's 3. So how did this exercise of proving things NP complete go from requiring the cream of the crop of academic computer scientists to high school students?
A lot of incomplete problems.
Right. As more problems are proven NP complete, it becomes easier to prove the next one because you've got a bigger library of things to choose from. So initially, the problems that were being proven were very different from each other. And over time, it just becomes easier because your library is bigger. So, we've already done a proof of NP completeness. If I back up here, right here, the subset sum problem is NP complete. And we showed how to reduce subset sum to this DAG half length problem. So what did we prove about the DAG half length problem when we showed there was a polynomial time reduction?
It's NP complete.
It's NP complete. We reduced a known NP complete problem to a candidate NP complete problem. If you can do that, you prove the candidate's NP complete. Now, how many of you took 1410 from me? Okay, so you may remember that I drill into the students what this is, right, in Java. What is this in Java? So what is the answer? 7 words. Anyone remember?
The object on which the method was
Yeah. The object on which the method was invoked. I guess that's 8. Okay. Okay, that's 1410. The thing I drill in this class is to prove a problem is NP complete, you reduce the known NP complete problem to the candidate NP complete problem. It's not the other way around. That question will be on the final. People miss it every time. There's no reason to miss it. You go from the known NP complete problem to the candidate NP complete problem. I'll explain why in a second. Okay. So now we're talking about proofs of NP completeness. And most of this is stuff we've talked about today. So just quickly, those are some of the NP complete problems. And over there are problems that are members of P. So these are the hardest problems from the set NP, and then those are easy ones from the set NP. This is why it works. So let's suppose X is NP complete. And let's suppose we show there's a polynomial time reduction from X to Y. Why does that let us conclude that Y is NP complete? Yeah.
Because if you can reduce everything from the left side into X, and then reduce that into Y,
Right.
all you're doing is just
about composition. The fact that X is NP complete means that every other problem from NP reduces to a polynomial time. So there, in particular, there's a reduction from E to X. Now, if we can find a reduction from X to Y, what's the reduction from C to Y then? Or forget about the reduction. Yeah. Don't forget about the reduction. What's the reduction going to be? You just compose the two reductions. You know, you take the input intended for C, you transform it to input intended to X, and transform that into input intended for Y, solve the problem, and transform it back. So you compose the reductions, and you're composing polynomial time reductions, you get a polynomial time reduction. So that's why we reduce from the known hard problem to the suspected hard problem, not the other way around. Yeah, the other way around. If Y was known, it's no big trick to reduce. If Y is known to be NP complete, it's no big trick to reduce X to it. We know everything reduces to Y if Y is NP complete. So you always go from the known NP complete problem to the candidate NP complete problem. Now, I don't want to mislead you. Because I sort of skipped past an important thing on the slide up here. A problem from NP is NP complete if you've got this reduction. So there's really two things you have to prove something's NP complete. You have to show that every other problem from NP reduces to it. And then you have to show that the problem Y is not too hard. You have to prove that it's a member of NP. Because there are problems outside of NP that are hideously hard that everything reduces to. So two things. It's got to be inside the circle first, and then you've got to show that it's everything reduces to it. Everything from inside the circle reduces to it. Yeah?
I was just wondering, is there problems outside of NP that can be verified in NP time? Sounds like
What define NP time?
well, exponential.
Yeah.
Like it would take exponential time to verify the solution.
Sure.
Which can possibly
Yeah.
generate the solution.
Yeah. There's a whole host of problems outside, not problems you tend to encounter many times in practice. But there are problems out there that require exponential time or double exponential time, or that can't even be solved on a computer. And that's stuff you talk about in a class like 3100. Here we're focusing on a much smaller set of problems. Okay, so we talked about polynomial time reductions, and there's a reduction we did. So what's the proof that if there's a polynomial time algorithm for some NP complete problem, then P equals NP? We talked about that, but it bears repeating. What's the argument that if you find a polynomial, I have a hard time saying that word, a polytime algorithm for some NP complete problem, then P equals NP? Yeah?
Because you can reduce any NP complete problem to another NP complete problem, and if you found the solution for one, you've found the solution for all of them.
Okay. So for P to be equal to NP, every problem inside the circle has to have a polynomial time solution. But if you can find a fast algorithm for any problem from NP, since anything from the set NP reduces to that NP complete problem in polynomial time, then by using the reduction and the fast solution for the NP complete problem, you can have a fast solution for any problem that you wish. And that's just what that says. So that's now, if P is not equal to NP, how can we argue that every NP complete problem requires exponential time? So the key thing is it's either they all require exponential time, or they all can be done in polynomial time. There's no halfway with these NP complete problems. What's the argument that says if you can prove that a single NP complete problem requires exponential time, then all the NP complete problems require exponential time? Yeah.
Does that have to do with the way that a reduction works? That if any of them are polynomial, then you're guaranteed to have a polynomial out, as opposed to if any of them are exponential, then you're guaranteed.
Yeah, I mean it does flow from the definition of a reduction. But basically, it's a proof by contradiction. Assume you got some NP complete problem X that has a fast solution. Okay? Now, we're assuming P is not equal to NP, so there has to be some problem Y from the NP that requires exponential time, otherwise P would equal to NP. So we've got this problem Y from the set that requires exponential time. We've got an NP complete problem X that has a polynomial time algorithm. Okay? But this problem Y has to reduce in polynomial time to X because X is NP complete. Through that reduction, you could obtain a polynomial time algorithm for Y, which is a contradiction because we assumed it was exponential. So our assumption that X has a polynomial time algorithm is wrong. Okay? So this is why most people believe that P is not equal to NP. Because it's got to be all or nothing. Either all these NP complete problems require exponential time or none of them do. And the bet is that if one of them could be solved in polynomial time, surely by now someone would have done it. And that's not a proof, it's just seems like the most logical outcome from this. Yeah?
So like with factoring, it wouldn't really help. It's not easy to prove that it's polynomial. You'd have to also prove that it's NP complete.
Well, no. Let's think about factoring. Suppose that we wake up tomorrow and the headline says P equals NP. Okay? Because someone has coded up a fast solution to the subset sum problem. What will that imply about factoring? Factoring is not NP complete. Factoring may not be NP complete, but it's a member of NP. And if P equals NP, everything in NP has a fast solution, including factoring. Now that wouldn't immediately tell you the fast algorithm for factoring, it would tell you it existed, but you could derive it by doing a reduction. Basically, all these proofs of NP completeness are recipes for you could use to construct algorithms if you ever found a fast algorithm for an NP complete problem. That's how you could solve all the other problems, by just composing reductions that were found by researchers. Okay, so proofs of NP completeness, we've already started doing them. They involve reductions. So you start with a known NP complete problem, reduce to the candidate NP complete problem. And all that leaves is, where did the first NP complete problem come from? Okay, so I'm just going to show this slide because this is what we've been talking about. Again, prove a problem is NP complete. First of all, prove it's a member of NP. How do you do that? Right. You argue its solution we verified in polynomial time. That's usually very easy. So the first step is to prove that it's not too hard. The problem is not too hard to be a member of NP. And then you pick a known NP complete problem and show that X reduces to Y in polynomial time. So 2 steps. First step is usually easy, and the second step is the tricky one. So next time we will look at a few more examples of proofs of NP completeness, and then we'll look at what Cook did to come up with the first problem.